Hi everyone, I'm Norwish and today I'm here with Suraj to present our Lab 13 machine case study for the Machine Design Lab. So we decided to study the grandfather clock, which was first developed in 1680. As you know well, its purpose is to keep track of time. The three machine components of the grandfather clock that we will talk about in this video are a helical extension spring, which is used for pendulum suspension. To suspend this guy, and threaded fasteners and gears.
Hey guys, it's Raj here. So now we'll start off with determining the mechanical advantage of the grandfather clock. To do this, we first have to define what the inputs and outputs of the system are. The input, or what provides energy to the system, is this weight over here, which generates a torque that drives the main gear. The main gear then drives all the other gears, which causes the clock hands to move as well as the pendulum to swing. Now you may wonder what causes the clock to move at a consistent rate slash what's the actual timekeeping mechanism of this system. This job is accomplished by the pallet over here we can see, which controls the speed of the escape wheel and hence all the other wheels or gears. So anyways, the mechanical advantage of this system is just the gear ratio between the main wheel and the minute or hour hand gears. For the minute hand, the main wheel has 80 teeth, whereas the minute hand gear has 24 teeth, resulting in a mechanical advantage of 3.33. For the hour hand, again, the main wheel has 80 teeth, whereas the hour hand gear has 48 teeth, resulting in a mechanical advantage of 1.67.
As mentioned previously, we were going to analyze three components of the grandfather clock. First is the spring, right here, which is used for pendulum suspension. This is better than, say, a hinge because the spring dampens the force transmitted from the swaying of the pendulum. The second component are the bolts. Over here, there are two bolts. One is here and one is on the other side. And the final component is the gears. Specifically, we will be analyzing only the main wheel down here because it's one of the most important gears in the system because it's what drives the clock.
Before we start analyzing the components, we will start by drawing free body diagrams. Since the extension spring is carrying the weight of the pendulum, the force applied on the ends of the spring is simply the weight of the pendulum. Of course, as the pendulum swings, this force may vary slightly, but for this analysis, we have decided to neglect this because we assume that this variation is small. Similarly, the force on the bolt is a shear force, and the magnitude of this force is half of the pendulum weight because the two bolts. This assumption is correct because the assembly is symmetric. Finally, the main gear is driven by a torque T, which is generated by the hanging weight. This causes there to be a force exerted on the main gear by the pinion that is connected to it.
Next, we'll determine some key characteristics of the components. Starting with the spring, for this specific spring, we found that its coil diameter is 1/8 of an inch, its mean diameter is 1 inch, it has 8 body coils, and it's made out of music wire, which has elastic moduli values of 11.75 MPSI and 28.5 MPSI. And lastly, this clock's pendulum weight is 100 pounds. As you can see in the formula for spring rate down here, we have everything except for the number of active coils, which we can determine using this relationship up here, resulting in 8.4 active coils. Plugging that into our spring rate equation, we found that the spring rate was about 42.6 pounds per inch, and using the relationship between force and distance for a spring, we find that the spring deflects by about 2.3 to 2.4 inches. For the bolts, its diameter is 0.2 inches. So with this, we can calculate the nominal shear force, which is just the applied load divided by the area. With this, we find that the nominal stress is about 1.59 kpsi. This value can be used to further find the maximum shear stress if the shear stress concentration factor is determined. Finally, for the gear, the driving force is the weight, which weighs about 5 pounds. The diameter of the shaft at which the weight is applied is 5 inches, and the diameter of the gear is 10 inches. Lastly, we assumed the pressure angle is 22.5 degrees. The input torque just equals the magnitude of the applied force, which is the weight, times the distance to which the force is applied, which is half of the shaft diameter. So we find that the input torque is 12.5 inch-pounds. And this should equal the radius of the gear times the tangential component of the force that the pinion exerts on the main gear. Solving for the tangential force, we find that this is 2.5 pounds, and using the pressure angle, we find that the force exerted on the main gear is about 2.7 pounds.
Being such an old and refined machine, it was difficult to find possible design improvements for the grandfather clock. So when we looked over the design, we believe that the area which has the highest chance of failing is this zoomed in area, because it has to hold the weight of the pendulum, which is large. Therefore, to reduce the stress concentration, we suggest for this area to have a large fillet radius. This corresponds with the force flow principle in shape synthesis design.
And that concludes our presentation. Thank you for listening.